Among the various kinds of disciplinary or shastric studies in Sanskrit, mathematics was considered both the art and the science of calculation. The Sanskrit word for mathematics, ganita, derives from the verbal root gan, to count, enumerate, or reckon, and accordingly, a mathematician or ganaka was a person who could calculate with numbers. The ubiquitous use of this ability to elicit knowledge via calculations earned mathematics its place as a superior discipline compared to other religious and secular fields of study. In the Prolegomenon of his seminal work, the Ganitasara Sangraha, the epitome of the essence of calculation, written around the middle of the 9th century of the Common Era, the Jain mathematician Mahavira described the preeminence of mathematics in 23 metrical verses, of which here are 2 examples praising its majesty, with perhaps a touch of poetic hyperbole. In speaking about mathematics, Mahavira notes, among prosody, poetics, and poetry, among logic, grammar, and other similar subjects, among all things that constitute the excellence of the various arts, the science of calculation is considered the most excellent. A little later in the text he adds, what is the point in rambling on endlessly? Whatever exists in all the 3 worlds, worlds that possess the things that move and are motionless, all of those things cannot exist separated from mathematics. The story of Sanskrit mathematics, however, is much older. It begins over 3,000 years ago in the hymns of the Vedas, praising, among other things, sequences of extraordinarily large numbers. For example, the Taittiriya Samhita of the Yajurveda, written around the 10th century before the Common Era, invokes successively larger powers of 10 from 100 up to 1 trillion, using specific words to denote the large numbers. Here is a recording of a passage chanted by an assembly of Brahmin priests from South India, invoking these large numbers.
Shadaya smaha, sahasraya swaha, yudaya swaha, niyudaya swaha, prayudaya swaha, budaya swaha, nirbudaya swaha, samudraya swaha, bhutjaya swaha, andaya swaha, paradaya swaha, shadaya swaha, vyishti swaha, deshidaya swaha, adhiraya swaha, didaya swaha, samajnaya swaha, lokaya swaha, sarvasmai swaha.
Numbers in their arithmetic offered an opportunity to the Vedic people to connect cosmic dimensions to their sacrificial rituals and propitiatory practices. Often, the types or goals of the fire sacrifices were intimately connected to the shapes of the sacrificial altars built from fire-baked bricks of specific shapes and sizes. For example, the image to the left of the slide shows the outline of the falcon-shaped fire altar built for the Atiratra Agnichayana Shrauta ritual, the overnight heaping of fire, performed as a symbolism of the sacrifice of the cosmic man, or Purusha or Prajapati, through which the universe was created and ordered, and his reordering to ensure the continuity of the seasons and the well-being of the ritual's patron or sacrificer. The dimensions of the bricks used in the construction of these fire altars often conformed to the measurements of the body of the sacrificer. The geometry governing their construction was determined by manipulating cords of various lengths attached to wooden stakes. Over time, the manual of these cord-based measurement techniques came to be known as the Sulba Sutras, the rules of the cords. The Bodhayana Sulba Sutra is one of the oldest versions of these manuals of cord rules, composed around the 8th to the 5th century before the Common Era, and it describes various area-preserving transformations of geometrical shapes like squares, rectangles, trapeziums, circles, etc. The knowledge of these transformations, although intimately connected to the construction of the fire altars, led to more general observations in geometry. For example, In the verses 1, 12 and 13 seen here, we find Bodhayana's expression of the Pythagorean theorem centuries before the birth of its eponymous Greek discoverer. Bodhayana states, "The chord equal to the diagonal of an oblong or a rectangle makes the area that both the length and the width separately make. By knowing these things, the stated construction is made." What is noteworthy in the history of the transmission of these Vedic texts is the preference of orality over the written word. The Vedas were meant to be recited, heard and memorized, and accordingly, their contents were composed in the format of condensed prosaic aphorisms or sutras, recited with precise pitch accent variations. The obedience of strict rules of recitation made it easy to memorize and transmit large volumes of text across generations largely uncorrupted, even if their laconic language made understanding their meaning often difficult. Various recitation styles were developed to aid in this process of memorization, many of which were codified by sequences of numbers. For example, the Jatapatha shown here is a style where a pair of words are repeated 3 times, with one repetition being in the inverted order. Let's listen in.
Tat savitus savitus tat savituhu savitur vare enyagum savitus savitur vare enyam bhargo vare enyam bhargaha Bhargo devasya bhargo devasya dhimahi devasya dhimahi.
The emphasis on recitation continued into the classical period of Sanskrit, following the standardization of Sanskrit grammar by Panini in his seminal work, the Ashtadhyayi, the 8 chapters composed around the 5th century before the Common Era. Increasingly, Sanskrit texts began to be composed in metrical poetry, with verses of different lengths in various meters, rather than in the short aphoristic style of the prosaic sutras. The sequence of light or unstressed and heavy or stressed syllables in each line of the verse specified its metrical signature. Here to the left we see the 8 possible combinations of a trisyllabic metrical foot or gana, where each type is denoted by a specific Sanskrit alphabet. For example, the Molossus meter, represented by the letter M, indicates a sequence of all 3 heavy syllables. The combination of these 8 metrical feet in each line of the verse indicated its specific meter. For example, in the verse shown to the right, each line has the sequence M, S, J, S, T, and a final heavy syllable. And this corresponds to the 19-syllabic Shardula Vikridita meter, the sport of a tiger. The combinatorial rules of calculating the distribution of light and heavy syllables in meters of various specific lengths was then as much a question of mathematics as it was, perhaps, of prosody. In fact, the challenge of composing metrical verses became a mathematical problem for many Sanskrit grammarians. For example, Pingala, in his Chanda Sutras, written around the 3rd or 2nd century before the Common Era, describes, although cryptically, the number of metrical patterns of a certain length that contain a specified number of light or heavy syllables. In modern mathematical parlance, this is the problem of finding a binomial coefficient, n pic p, where p, the number of light or heavy syllables, is an integer lying between 0 and n, the total number of syllables. As we see here, Pingala simply claims next full, and so on. His commentator Halayudha, from around the 10th century of the Common Era, interprets these 2 sutras as generating the Meru Prastara, the pyramidal expansion or the so-called Pascal's triangle. The sequence of internal numbers in each row of the pyramid is generated by summing the diagonal entries from the previous row. For a meter of 4 syllables, the entries in the 5th row of the pyramid indicate that there are 2 combinations of all 4 light or heavy syllables, 4 combinations of 3 light and 1 heavy syllable, 4 combinations of 3 heavy and 1 light syllable, and 6 combinations of a mixture of 3 light and 3 heavy syllables. In total, there are 16 possible combinations of light and heavy syllables in a meter of 4 syllables. Around the middle of the first millennia of the Common Era, Sanskrit astral sciences, or Jyotisha, became the primary vehicle for the advancement of mathematics. The growing complexity of astronomical computations, in particular, those involved in determining the true positions of the planets and the times of the eclipses, required more advanced numerical and geometrical techniques. Increasingly, mathematical ideas were elaborated in canonical astronomical treatises or siddhantas, composed in an assortment of metrical stanzas called padyas, each with their own inherent rhythmic pattern. For instance, Aryabhatta, in his Aryabhatiya, written at the end of the 5th century of the Common Era, describes an algebraic method to find 2 unknown quantities, knowing their difference and their sum, in a verse composed in the Arya meter. The Arya meter is an extremely popular Moraic meter that can be recited in several ways. Here is one such recital in the fast 16-beat rhythmic cycle called the Drutalaya Tritala.
Tvikriti gunat samvargat Tvyantaravargena samyutan mulam Antarayuktam hinam tad Gunakara dvayam dalitam.
Indeed, the parsimony of poetic speech often meant that authors themselves, or sometimes later writers, had to write various kinds of prose commentaries, called vyakhyas, tikas, bhashyas, udharanas, etc., to explain the mathematics expressed in the terse metrical verses of their canon. This system of writing metrical base texts and subsequent prosaic commentaries constituted much of the standard didactic of technical literature in classical Sanskrit. The emphasis, however, remained on a verbal presentation of the content, a sort of running commentary. For example, in his commentary on Aryabhatta's aforementioned rule to determine 2 unknown quantities, Bhaskara I glosses the word of the base text to explain their meaning. The style of Bhaskara's exposition is extremely didactic. First, individual words are explained, and then their meaning is brought together to understand the sentence. For instance, to explain the expression Dvikriti gunat samvargat, Bhaskara I says, Dvikriti is the square of 2, that is 4. Dvikriti guna is that which has the square of 2 as the multiplier. Therefore, the word Dvikriti gunat, with the square of 2 as the multiplier. What has this as its multiplier? To this, he, Aryabhatta, said samvargat, of the product of 2 quantities. In effect, Bhaskara I passes Aryabhatta's expression Dvikriti gunata samvargat as meaning, quote, of the product of 2 quantities with the square of 2 as the multiplier, end quote. Simply put, 4 times the known product of the 2 unknown quantities. The connection between poetry and pedagogy is perhaps best demonstrated in the works of the Sanskrit astronomer and mathematician par excellence, Bhaskara II, commonly called Bhaskaracharya, or Bhaskara the teacher, who flourished in the middle of the 12th century of the Common Era. His text on arithmetic, called the Lilavati or playful, and on algebra, called the Bija Ganita, or computing with seeds, are considered two of the most celebrated texts of medieval Sanskrit mathematics. In fact, the renown of these texts meant that they were repeatedly translated into several vernacular and foreign languages up until the end of the 19th century. The mathematical examples in these texts are posed as questions composed in a variety of melodic meters. Their dialogical style is one of the main reasons these texts held their appeal for generations of learners of Sanskrit mathematics. For example, as we see on this slide, Bhaskaracharya poses the question of determining an unknown quantity in his Leelavati with some rather vivid imagery. In this verse, Bhaskaracharya inquires of a mathematician what the total number of pearls on a young woman's necklace is when fractional parts of that total are scattered all around as the necklace breaks in the act of lovemaking. This verse is composed in the 21-syllabic Sragdhara meter with a caesura of 7, 7, 7. Let's listen in.
हारस्तारस्तरुण्या निधुवनकलहे मौक्तिकानां विशीर्णो भूमो यतस्त्रिभागः शयनतलगतः पञ्चवांशोऽस्य दृष्टः प्राप्तः षष्ठः सुकेशा गणकः दशमकः सङ्गृहीतः प्रियेण दृष्टं षट्कं च सूत्रे कथय कतिमपैर्मौक्तिकैरेष हारः.
In the world of metrical mathematics, expressing numbers, especially large numbers, posed a unique challenge when confronted with the poverty of appropriate syllables available to express them. This challenge became more acute when stating large astronomical and mathematical parameters within the syllabic constraints of the meter. However, Sanskrit astronomers found ingenious ways to circumvent this problem by codifying numbers using various systems of alphanumeric enumerations or chronograms. One such system was the Bhuta Sankhya system of object numerals, where ordinary words or classes of words came to represent numbers. For example, all synonyms of eyes or hands, objects ordinarily occurring in pairs, denoted the number 2, while all synonyms of fire denoted the number 3, based on the 3 types of sacred fires lit in every Brahmin's house. Many of these word-number associations were based on historical, mytho-religious, and socio-cultural ideas commonly known across the Indian subcontinent. The use of these word numerals even allowed Sanskrit mathematicians to present versified versions of numerical tables. For example, Lalla, in his Shishadi Vriddhida Tantra, the treatise that expands the intellect of students, written around the late 8th or early 9th century of the Common Era, gives the values of the trigonometric ratio sine corresponding to every successive 24th division of an arc of 90 degrees. The sine values are expressed in the Bhuta Samkhya numerals in 3 verses composed in the 12-syllabic Vamshasthavila meter with a caesura of 5, 7. Here is a recital of the first of these 3 verses.
क्रमार्ध जीवाः शरनेत्र बाहवो नवाब्धिवेदाः कुशलोच्चयर्तवः खनन्दनागाः शरशून्यशूलिनः शरेन्दुविश्वे नखबाणभूमयः.
Other Sanskrit astronomers contrived other systems of alphanumeric enumeration to represent large astronomical parameters in their texts. For example, Aryabhata II, who flourished around the middle of the 10th century of the Common Era, in his Mahasiddhanta, or the Great Treatise, used a variation of the Katapayadi system to represent integer number of revolutions of the planets in periods of 1 kalpa, where a kalpa is a period of 4.3 billion years. The Katapayadi system is a system where the 33 Sanskrit consonants are successively mapped to the individual decimal digits. And while the system allowed for conciseness and versatility in setting large numbers to meter, it often meant that the verses contained sequences of nonsensical syllables that were simply unmemorable. For instance, here on the slide we see Aryabhata II's use of the Katapayadi system in his Mahasiddhanta to indicate the number of revolutions of the sun, the moon and Mars in one kalpa. His syllabic sequences, while metrically sound, are semantically meaningless. The string of consonants gha, da, fe, na, ne, na, nu, ni, na indicates 4,320,000,000, while the string k, kh, jh, ta, jo, gi, pa, ni, no, na indicates 2,296,831,000. In comparison to the concrete object numerals of the Bhuta Samkhya system, the encoding of numbers using the Katapayadi system didn't quite gain widespread use among medieval Sanskrit astronomers, with the exception of perhaps the astronomers from the Neela school in South India. The object numerals offered a more convenient and meaningful way to include numbers in various mathematical statements that sometimes included ingenious algebraic insights set to the most commonest of meters. For example, Bhaskara I, who we encountered earlier as the mid-7th century commentator of the older Aryabhata from the 5th century of the Common Era, wrote a more extensive work called the Mahabhaskariya, or the Great Work of Bhaskara, in the early parts of the 7th century of the Common Era. In this work he describes, rather remarkably, an approximate quadratic expression for the sign of an arc in degrees. Bhaskara's work may have been arranged to the most common 8-syllabic Anushtup or Shloka meter, the most common meter found among the verses of the Bhagavad Gita, but the mathematics they describe is anything but common.
Chakrardham shaka samuha dvishodhyaye bhujang shaka tachesha gunita dvishta shodhyaha khabreshu khabditah chaturthamshena sheshasya dvishtamantya phalam hatam.
And while these sonorous recitations served as a mnemonic to recollect the general procedure, they often required a more nuanced understanding to fully appreciate the subtle algebra. Just looking at the slide, we can see how rendering the awkward English translation of Bhaskara's Sanskrit verse into modern mathematical notation is not a simple task. Often, we find that what was gained by the beauty and brevity of the meter gets lost in the breaks and the brackets while explaining the matter. This competition between meter and matter allowed Sanskrit astronomers to be very creative in the ways in which they presented their mathematics. As we have seen and heard thus far, encoding numbers became vital to describing mathematics in metrical poetry. Likewise, arithmetic operations like addition, multiplication, division, etc. required a large artillery of synonymous words to include them in meters of various lengths. The inherent polysemy of words in Sanskrit, words that are derived from various verbal roots, allowed Sanskrit authors to manipulate their use as they deemed necessary. For example, we see on the slide a selection of word forms used to describe the operation of addition by the older Aryabhata, known as Aryabhatiya, written at the end of the 5th century of the Common Era. The freedom to choose words ad libitum allowed these authors to play on their meaning in more ways than simply conveying their mathematical intentions. And perhaps one of the finest examples of this numerical poetry can be seen in the writings of Nilakantha Somayaji, a 15th century commentator on Aryabhata's Aryabhatiya and a famous proponent of the Neela school of medieval Keralese astronomers and mathematicians from southern India. Right at the very beginning of his seminal treatise on astronomy, the Tantra Sangraha, Nilakantha offers what appears to be a homage to his chosen deity, Vishnu, also called Narayana.
He Vishnu nihitam kritsnam jagatvayeva karane jyotisham jyotishe tasmai namo narayanayate namo narayanayate.
However, when the words Hey Vishnu Nihitam Kritsnam, O Vishnu embodied in you, is interpreted with the Katapayadi system, it denotes the number 1,680,548. This number is a hidden astronomical parameter. It indicates the number of civil days since the beginning of the Kali Yuga or the epoch, conventionally considered as 17th of February in the year 3102 before the Common Era. In Gregorian dates, this number corresponds to the 22nd of March, 1500 of the Common Era, the date on which Nilakantha composed his Tantra Sangraha. The history of Sanskrit mathematics is a history that runs its course following the ebb and flow of innovation, inspiration, and imitation. As mathematical ideas from within and beyond the borders of India came to cohabit the minds of medieval Sanskrit mathematicians, the language they found to express themselves flirted with poetry in ways that enriched their thinking. Poetry became the vehicle of thought instead of an embellishment to it. And it is in this fact, if not in much else, that Sanskrit mathematics allows us to see how mathematical insights can be conceived and conveyed in modalities very different to what we are commonly accustomed to. It is my hope that the short presentation inspires you to think of mathematics beyond the trappings of symbols and equations, and reaching out to the meters and melodies of poetry to give it voice. I thank you for your patience.